Alrighty, so today we are going to be looking at that article we found yesterday. This is a article on ray marching, written by Michael Walcyzk. I don't exactly know, but you can feel free to follow his GitHub. It's MWalcyzk. Cool. So he has a bunch of code here. What we're gonna do in order to kind of make sure to kind of really internalize what's inside this article is we're gonna rewrite this code in Python. So I think by the end of it, it'll be some small amount of code. Yeah, however many lines that is. So yeah, we'll try to write it in Python. Obviously it's not going to be a one-to-one thing, but it should help us. So we're going to go here in our VS Code. Inside better, let's make a new file here. Let's call this raymarching.py. All right. And while we're at it, why don't we also pyenv, nope, let's grep our history for pyenv, because I always forget the command to create a virtual M. We'll go ahead and create a virtual M. This one we'll call it ray marching. And then we'll pyenv activate ray marching. Okay, so now we're inside of a new Python virtual environment, and we are inside the folder. We can do Python raymarching.py, doesn't do anything. Print hello world. All right, so we're good to go. Let's go ahead and give this a toy implementation of ray marching. Look at that. GitHub Copilot wants to say in Blender. Interesting thing to think about. Okay. Let's import numpy as np. And yeah, why not? PLT, and then kind of at the very end, I think we'll do something like imshow, right? np dot array 1010. I think probably also need import PIL. Let's see, Python image library render numpy. Convert a numpy array into an image. Actually, right here, minimal code for rendering a numpy array as an image. Yep. Let's go back. Or PIL dot image. Right, then we're gonna have PIL dot image dot from array. We don't need test dot png. Actually, that's a better way to do it. We don't need PIL, just need image. Then we're gonna save test png. Go ahead, pip install numpy. let's pip install Python image library. It's pillow. Pip install pillow. Alright, and then matplotlib. Probably this one. Okay, back to here. We'll close this. I think we might need to cast this to a uint array. Let's go ahead and run that. Could not interpret 10 as a data type. Mesh grid. That's what we really want. List has no attribute. Array interface. So AS type. Let's go back to here. uint 8. uint 8. List object has no attribute as type. np dot array of that. Damn. My NumPy is real rusty. Create an empty image NumPy. Okay. Let's get rid of this weird AB crap here. Image, we get it from A. Ooh, we have caps lock on, get it from A. A equals np dot zeros, yep, 100. How about we say something like image size up here, and we'll say 100. Image size W, image size H. Also, let's say 256. 256. Let's do some typecasting here. Let's do int. Or not some typecasting, but explicit typing. NP zeros, we want dtype to be uint 8. Alright, now let's try. Alright. And then here, if we open test, Control B, it should be in here. Yeah, here it is. All right, there we go. We have this code generates this black image right here, and if we do ones, then it's going to now it should be a white image. this. Is the matplotlib. Okay. There's no E. Okay. Alrighty. So we have some code there. Display with matplotlib save to image. Okay. I think this is complaining here because it's not the right PyEnv. We want it to use what do we call our PyEnv? Ray marching. Okay, we want dot PyEnv interpret. We want this, but not that one. PyEnv versions dash 3.9.1 slash ems slash ray marching how do you do that? Show location of Python PyEnv. PyEnv versions. PyEnv versions. It's on ray marching, but maybe it's just because we need to close this. Let's reopen. I think if it, let's see if it's actually smart enough to do that. So will no, it will not. I was wondering if, there we go, if VS Code would be smart enough to automatically update the environment and based on where you open the workspace, but that is not the case. All right. Let's go back to the ray marching. We're getting distracted here. Okay. If you've ever visited ShaderToy, you've probably seen ray marching in action. It's an interesting technique that can be used to generate fully procedural environments entirely from a single fragment shader. Unfortunately, there isn't a ton of great resources for learning these techniques. Basic ray marching shader. Using derivatives touch designer, but you should be able to do this with any other 3D environment fairly easily. Okay, when we use ray marching, we aren't dealing with polygons anymore, so a lot of the things that we're used to in a typical 3D toolkit, geometry, lights, camera, are non-existent. Okay, if we don't have points, how do we do anything? So the trick is to use signed distance function. So signed distance function is the orthogonal distance of a given point x to the boundary of a set in metric space, with the sign determined by whether or not x is in the interior of that space, of that set. So the graph in the bottom in the red of the signed distance between a fixed disk top and a point of the plane containing the disk, blue. Okay, so basically, what is this plot, right? What is going on here? So the top shows this disk, which is basically laid on this surface, this plane, and then the red shape here represents the distance at each xy point, right? So the xy coordinate is the point, and then the red, which is the z, tells you how far away that xy point is from the disk. So objects, the point in the very middle of the disk is exactly one radius of the disk away from the disk, or from the plane, and so on. And you see here with this little oblong figure 8 shape, you get a slightly different signed distance function. So signed just refers to the fact that it is negative and positive, right? So you have some values here inside the circle are inside, positive, and everything else is negative outside, right? So you can not only indicate the distance of a point on the plane to the actual shape, but you can also indicate whether it's inside the point, or inside the shape, or outside the shape with the sign. Okay. These are mathematical functions that take a point in space and tell you how far that point is from the surface. Let's say we have a point in 3D space in the specific render toolkit that they're talking about here, Derivatives Touch Designer. What is this? Learn, Touch Designer, Touch Designer. Visualizes data step, data flow. So this is some kind of OpenGL, Vulkan, some kind of rendering for live shows. IDPI panels, okay. So some kind of art rendering software that seems to be used for live concerts and the such. Okay, so he's saying let's make a point in 3D space. So let's go ahead and do that. Let's define a P. This is going to be an ND array. Look at that, we already have this point in 3D space here. In fact, we can actually do exactly what they're saying there, x, y, and z, and then we have x, y, and z equal, I don't know, 1, 1, 1. Vector in 3D space. Fake image. Okay. Suppose we have a sphere centered at the origin with unit radius. We want to answer the question, what is the distance p? What is the distance from p to the closest point on the sphere? Okay, it turns out that this distance corresponds to the length of the vector that points from p to the sphere's center minus the radius. Okay, so we have a function that we're going to call distance from sphere. This function is going to take in a, look at that, look how smart Copilot is. This is crazy. It's basically written this function for us. We have P ND array, center ND array, and we have the radius, which is a float. It outputs float. It gave us a nice little doc string here, distance from sphere, and we simply return the P, the point in the space, minus the center, and then subtract the radius. And this norm function, I think, is what the length is doing. Yeah, if you aren't convinced, check out the diagram below. Here, P denotes the length or norm of the vector P minus C, which points from the center of the sphere C to P. Convince yourself that the P minus C does in fact give you the point, the code snippet. This function is signed because it returns a negative value or a positive depending on whether we are inside on the surface or outside the sphere. Yeah, so depending on where this point P is, if this point P is inside the sphere, P minus C is going to be small. And when you subtract, it's going to be smaller than the radius, and when you subtract R, you're going to get a negative number. If P is significantly, or is outside the sphere, P minus C is going to be greater than the radius. So when you subtract the radius, you're going to get a positive number. Okay. In order to render our scene, we're going to use a technique called ray marching. At a high level, we will shoot out a bunch of imaginary rays from a virtual camera that is looking out at our world. For each of these rays, we are going to march along the direction of the ray, and at each step, evaluate our signed distance function. So this will tell us, from where I currently stand, how far am I from the closest point of the surface of our sphere. Okay. So, nerve ray marching. I really like this this image. So maybe this one? No, I like this one better. Right, so we're going to be shooting out a ray from our camera, and we're going to be evaluating the value of our signed distance function at each point along that ray, right? So in this case, the signed distance function evaluated at each of those black dots is a neural net, which returns four numbers, the color and the density, RGB and sigma. But in our case, the signed distance function is simply going to be this simple distance from sphere function that we created. So let's go ahead and define another constant here. We'll call it step size. And this is also going to be a float, and this is going to be 0.1. Okay, I think there's a way. What's the shortcut here for format? Format document, Control-Shift-I, Control-Shift-I. Ooh. Install AutoPep 8. Alright, there we go. Now we are ready to rumble. Okay. So this is just a for loop. Okay. 4. Damn, look at this. Look at GitHub Copilot literally writing ray marching for us. This is absolutely insane. Alright, but that's not what we want to do. We just want to look at one ray coming out, right? And that ray is just going to be based around the number of steps. So we also have another variable here called number of steps. Let's just say something like 100 to begin with. So for I in range number of steps, I don't want all of this, but D is equal to the current position. So let's actually call it what they call it here. Current position, which is going to be an ND array. This is going to equal R naught, the ray's origin and direction. Ray origin plus ray direction times I times step size. Yep, that is correct. Get rid of that. Turns out that a much better approach is to use distance-aided ray marching, sometimes called sphere tracing for some reasons that we will see. At each position along our ray, we evaluate our signed distance function, which by definition gives us the distance to the closest object in our scene. We treat this distance as the radius of a sphere centered around our current position. Okay, so here they have a camera shooting out a ray, and you're sampling the signed distance function at those points in the ray. Virtual camera, the red line represents a single ray. The green mountain represents a more complex object. Okay, so we assume we have an SDF that represents this shape. Okay, so the signed distance function is this shape. Each position where we evaluate our signed distance function is represented by a small blue circle. So the signed distance function, if you evaluate it at this blue circle, is going to give you basically the value of this gray circle, because that signed distance function represents this green geometry. In the order drawn bottom to top, each X represents a point on the surface that is closest to the corresponding blue circle. There are two large optimizations that we can add to this. If our SDF returns a very small distance, we will consider this a hit and break out of the loop early. The second involves rays that never pass through any object in our scene. If our ray marching, we can keep track of the total distance traveled thus far and break out of the loop if we hit a certain threshold. So rather than just moving forward a certain number of steps at a certain step size, he's basically what he's basically saying here is just bound it based on kind of a distance from the camera. If your signed distance function is very small, that means you hit something, so then just stop evaluating. But then if you go too far, then also stop evaluating. Okay, so evaluate the SDF at various points along a ray. But now what we're going to do is we're going to define a ray march. There's going to be a ray origin, a ray direction, and it's going to output an ND array. So this is actually correct. Let's see if GitHub Copilot also creates the correct function here. Right, so this is more of kind of an explicit language here, so they have to actually initialize some things. We can actually initialize those up here with our constants. Number of steps, they have 32. Let's change this to 32. There's a min hit distance. That's going to be 0.01. And then we're going to have a max hit distance. And that's going to be 1000.0. Both of these are floats. Total distance traveled here corresponds to what GitHub Copilot called total or distance here. For I in range number of steps, so Copilot again recreated it took our number of step variables and recreated that. This is really crazy stuff here. Then it has a current position, and that is the ray origin plus the total distance traveled times RD, which is ray direction. Okay, so there is a difference here between what Copilot is doing and what this code here is doing. It is evaluating our distance from sphere, giving it the current position, P. What is P in this case? Vec3 of 0. Distance from, so P just refers to a point here. This is the distance from sphere of a point. Center is the position of center of sphere, and that is what we want to put here. And then the radius of the sphere. We can actually, let's get rid of that. Or we can actually just make it explicit. Radius of sphere. And that's going to be float 1.0. And we'll go ahead and replace that there. Okay. So what is this return? This is returning a color. ray march turns a color, right? Three-dimensional RGB color. So there's going to be a couple different edge cases here. This is going to be hit an object. SDF is very small. SDF is either close to 0 or negative, right? Ooh, we don't want to do this. And then we have another edge case here where missed the object missed all objects. Our ray is going further than we want, right? So if the distance is greater than the maximum hit distance, then just break. And in this case, return empty. So this will be no color, right? Black. Or actually, we can actually set this explicitly. Let's say color background. And then let's say color object. Okay, if we hit something, we're going to return our object color. If we do not, we return the background color. I think this is a cleaner way of doing it, honestly. And we will calculate so in GitHub's Copilot, they don't have this accumulating total distance traveled. So we can go ahead and make that an accumulator. Total distance starts off at 0. Then down here you have total distance plus equals distance, right? Add accumulated distance. Now I think I know why I like this pattern better, because it could return none, right? Versus if you always return color background, then that's a good default case. And then your current position is going to be the ray origin plus total distance traveled. And we don't actually need I at all. Let's get rid of that. Alrighty, so we have our ray marching. How do we generate our rays? Okay, so now we have an actual rendering function that, okay, given a ray origin and a direction, gives you the color. But we don't know how to generate these rays, right? There's going to be a bunch of rays. There's going to be a ray for each pixel. An origin and a direction. We're going to imagine that each ray starts at the camera and passes through an imaginary image plane that is somewhere in front of our camera, right? So here's the camera right here, and then each ray passes through the image plane and goes into the scene. And the intersection point of that image plane and the ray is going to be where we put the color, and that's how we're going to get the image. All of our code will execute inside a single fragment shader, so there's a bit of a leap. We have to somehow describe a 3D world from the 2D plane that our fragment shader executes. Once for each pixel that makes up our final. At each pixel location, we can derive a UV coordinate in the range 0, 1. Okay. You'll be able to draw normalizing, blah, blah, blah. If you are rendering an image that is not square, you'll take into account aspect ratio, blah, blah, blah. Okay. Let's remap our UV coordinates from the range 0, 1 to -1 to 1. Okay, yeah, so let's say the camera is 5 units away from the origin in the -z direction. Yeah, so there's a couple different parameters that we're going to have to add here. Right, we have the center of sphere, we have the radius of the sphere, then we're also going to have to say center camera. Or what about pose camera? Wow, that 5 units away from the origin in the -z direction. Look at that. It's not quite -5, but that is creepy how good GitHub Copilot is. Okay, so we're -5 units away from the image plane. The sphere itself, let's say the center of the sphere is another 5 units away from that. And then we're also going to need the UV coordinates. I think what they mean by UV coordinates is basically the image plane coordinates. Are not camera position vect RD, so the radius, the ray direction equals UV 1.0. The Z coordinate of the direction ray acts sort of like the camera's FOV, pushing the image closer or further away from the camera. Okay, for now we will leave this at 1.0. So since each fragment has a unique UV coordinate, each execution of our fragment shader will generate a unique ray. Okay, keep in mind that because the way shaders execute, all these calculations will be happening in parallel. They will not for us, unfortunately. Now that we have a way to generate a unique ray at each pixel, we are finally ready to ray march. Okay, so let's get rid of some of this stuff here. We don't need this anymore. We don't need this anymore. Okay. We're going to Control-Shift-I, format it, make it look nice. All right, so now what we're going to do is we are going to generate all the rays coming from the camera. So we're going to generate a grid of points in the image plane, first of all. We're going to use an MP mesh grid, so ND coordinate arrays from vectorized. Okay, so you give it XY mesh grid. Okay, this is what we want here. 2 lin spaces, and then a mesh grid of both of those. Okay. So NX and NY is going to be the number of points. So what we're going to do is we're going to just put this directly in here. And here we're going to have the image, what are we saying? X is height? No, X is width. And then Y is height. I will be back 1 second here. All right, we have returned. Cool, so we were creating this mesh grid which represents every point along this image plane. We have the center of the sphere, the radius of the sphere, the position of the camera. Let's make it a little bit more consistent, and then we're going to have maybe center of image plane. That's going to be right at the origin. Yeah, and then here we're going to have image plane size in X, and we're going to have image plane size in Y, and here we're going to go from negative image plane size X over 2 to positive image plane size X over 2. And it's going to be the same thing here except Y. Alright, so our image plane is going to extend from negative bounds to positive bounds, right? Negative Y to positive Y, negative X to positive X, and we're going to break that space into the number of pixels, in this case 256 by 256. And we're going to create a mesh grid from that. So what does mesh grid return? Coordinate matrices. Okay, so then you can kind of use a nested loop here. Generate all the rays coming from the camera. Okay, so we're going to have image size W. We're going to do image size H. W is X, or width is X, height is Y. X, no, we can't rewrite that. Let's recall this image X, image plane X, and image plane Y. So then image plane X at this should just be one. This should just be one list of. I'm confused. Let's actually look at what this does. I'm starting to confuse myself here. Okay, so yeah, we create a 3x2, so when you actually want to reference this number, it's going to be at position that, at position that. Right? And image plane Y also at that. So this is going to be the X point and the Y point, and the Z point is going to be the center of the image plane, right? Center of image plane. We'll say 0 plus the X. Ooh. We'll say center of image plane 1 plus the Y, and then we'll say center of image plane 2, which is the Z coordinate. So ray direction, which is equal to an NP array, is going to be this. Or no, that's going to be the image plane position point. All right. Then there's going to be the center, ray center is going to be the center of the camera. Ray direction is going to be the image plane point minus the ray center. And ray direction, I think this needs to be normalized, so let's go ahead and normalize that. np.linalg.norm. All right, and let's go ahead and let's create our fake or empty image buffer, right? We'll call this image, and this is going to be, of course, in the size image size W, and then image size H. These might be flipped. But luckily we have a square image, so it doesn't matter. It's all the right size. So now that we have the point on the image plane, we have the center of the camera, we have the direction that goes through that point in the image plane, we can go ahead and calculate our ray march. So the image at coordinate X and coordinate Y here, right, is going to be ray marching with the ray center or ray origin here, and then ray direction. And if this immediately works, that will be very curious. It does not. All right, good to know. Okay. Each fragment has unique UV coordinates. Each execution of our fragment shader will generate a unique ray. Keep in mind that because of the way shaders execute on your graphics card, all these executions will be happening in parallel. We have to generate a unique ray at each pixel, and we are finally ready to ray march. Now we have all the pieces we need to write our first complete ray marching shader. At each pixel location, we will generate a ray, which we will use inside our ray marching routine to map our 3D environment. Okay. So I wonder if we can use total distance is not defined. How do you run Python file? How about debug Python file? Okay. So I think if we put a breakpoint here, it's been a while since I've breakpointed inside of VS Code, but let's try to make this a little bigger so you can see better. Is there also a shortcut for running and debugging? Let's put a breakpoint there. All right, here we go. This is what we wanted. We wanted this. All right. So color object, all of our big variables. These are the variables that we're a little bit more interested in here. The image plane. Yep, you have a 256 by 256. Maximum, minimum goes from -1 to 1 on both of those. Okay. If we step into, no, we want to step over, image plane point, globals, image plane point, why is that not, okay, there it is. It's starting at the very bottom, -1, -1, 0. The ray center is at 0, 0, -5. Right? The ray direction, okay, it's not linalg norm, it's going to be ooh, shit. Let's do that. And then let's get rid of this breakpoint here. Still not getting that red that we want. Let's make this ray direction, and then let's say ray direction equals ray direction divided by the linalg norm of ray direction. Again, not really showing us what we want to see here. Okay. So march from the ray center to the ray direction. Let's make this something much more manageable. Let's just make this a 3x3 image. Image plane size, let's do 1.0. Smaller sized plane. The center of the camera is at -5. The center of the sphere is at 5. The center of the image plane is at 0. The background color is black. The foreground color, also an NP-ND array, is red. Now let's go ahead and run this. Close out of this crap here. Oh, look at this tiny little image. Okay, let's import PDB, pdb.setTrace. I think actually, we don't even need to do that. We can just say breakpoint. Right? Modern Python. All right. All right, so actually we are correctly rendering here. What's not happening correct is the image from the array. Image from array PIL. Ah, 255, that's what it is. Actually, let's do that. Okay, so there we go. That's what we wanted. All right, so basically the problem was that the array that you feed into the Python image library needs to be 0 to 255, right? It's a unsigned integer array where 0 represents black and 255 represents white or maximum, right? So we were just rendering zeros and ones, which are basically very, very slight different shades of black, but we want actually 255. So we can probably actually do this, and then we don't need to do it here. Let's go ahead and make this big again. 256 by 256 will make the image plane a little bit bigger as well. And now let's render it. Notice how much longer it takes to render now, the 256 by 256. Look at that. We have our red image. Perfect. Okay. So let's go back to here. And now we're going to be looking at shading. So now we have our sphere. Let's try to calculate some basic shading so that it's a 3D surface. If you're familiar with diffuse specular, you probably know that we need normal vectors to calculate shading. For a sphere, the normal at any point on the surface can be calculated by simply normalizing the vector center minus the p. Whereas before, C is the sphere center and P is a point on the surface. However, this method is limiting and doesn't extend to other shapes. Makes sense. So the normal is merely the vector that comes out of a surface, right? Normal vector. So yeah, for a sphere like this that is made out of these little squares, which are basically the base primitives inside what's called a mesh, which is a 3D format, right? Each of these little squares, there's a line that points perfectly out that makes right 9-degree angles with the plane of that, and that is the normal. If you have a perfectly symmetrical shape like a sphere, you can basically have infinite precision in the like the normals, but normally things are made out of meshes, so the normal is based around the triangle, right? That little individual triangle or square in the mesh. Okay, we need a more dynamic way of calculating. The idea is we nudge our point P slightly in the positive and negative direction, recalculate our SDF, and see how the values change. Okay, we're actually calculating the gradient of the distance field at P. Okay, so they're just replacing the sine distance function with a sphere. Okay, and now they want a normal function. So we're going to create another function here called normals on sphere. Let's see what Copilot auto-completed for us. So we have our point, we have our center. This returns an NP-ND array. Normals on the sphere of a point. It takes the point and minus the center and then divides by the norm, which is, I think, the correct thing to do there. However, this is just for a sphere, so we want normals on normals derivative trick. And we're going to do something similar here too. We're just going to take the point. So this is the trick that he was saying, where you can basically go a little bit up and a little bit down on the sine distance function. Normals calculated with a derivative trick. And then we'll make a separate SDF function, like they make their point ND array. This doesn't return a float. This returns a np.nd array. Or no, it does return a point. Sine distance function returns a single number. Yep, and right now this just returns distance from sphere, but eventually you can add more things. Okay. So the normal at the derivative point is going to be, there's going to be some small normal derivative delta. Oh, normal derivative delta. There we go. And we're going to add this point map the world. So this is our SDF function at the point plus the small step, and then minus the small step. Okay. np.nd array. There's going to be 3 parts to this. We're going to, wow, look at that. Copilot coming in again. We're going to evaluate the sign distance function at the point plus this delta and then minus that delta. And then again, the same thing, but for y. And then the same thing, but for z. And that will give us np. So this is going to be the normal vector, and then we want to return the normal vector that is normalized. All right. So they use some syntactic sugar called swizzling. Cool. Calculated, then blah, blah, blah. Okay, so we're going to replace distance from sphere with our sign distance function. Let's go ahead and format this. Go ahead and remove these breaks just because we're professional. And instead of the object, if you're close to the object, so let's define that distance, min hit distance, just so we don't have any magic numbers anywhere, you know. Min hit distance. So if we are smaller than the min hit distance, now let's calculate the normal vector at this point. Okay. And normally the normal vector will allow us to calculate what the light is going to look like at that point, but in this case we're just going to create something that has normal, something that just kind of depends on it but doesn't necessarily represent lighting. So we're going to say, let's just return this normal vector times, I don't know, 250 or times 0.5 here plus 0.5. And we're going to have to times 255 here, just because we're going to be doing things in floats, and then it's going to be easier. SDF takes 1 positional argument, but 3 were given. Yeah, so we can get rid of this curpose. Okay, and we can add that as default arguments to this. Goals, center of sphere, and then here, radius of sphere. And then we don't need to have them here because the default quark values are already provided. Let's go ahead and format to make it look pretty. Go back to our ray marching, run it. Float 64 cannot be interpreted as an integer normal vector. Normal linalg.norm np.array. So I think these are not point. Curpose, ray origin plus ray direction plus ray distance. What is going on here? All right, so point is a number. What happens if we go ahead and copy this line here? That's a number. This minus that is also a number. All right, if we hit next, next, what is normal vector? So I think the problem here is that, yeah, this is, we need to typecast these into Python floats. Yeah. So you would never do this in actual code because this is incredibly slow. Right? You'd want to you wouldn't want to be typecasting. In actual rendering engines, this is going to be all vectorized and parallel mapped float object. Let's make it a float 64. Because this is np.array, maybe that's all that we had wrong. Maybe we don't need this float 64. Maybe we don't need this float here. Now let's try. Yeah, we don't need any of that. Okay. Again, we're getting this black image. What's going on here? Multiplying by 255. If distance is less than mid-hit distance, let's do that. 0.1. We're going to get the normal, that normal vector is normalized. What do we just do this? Just the normal vector, and we just plot basically the normal vector. So let's go ahead and breakpoint here again, just to figure out what's going on, why this isn't working. and we're curious about the image. The image is just a bunch of zeros, so let's go ahead and make this rendering small again. We're going to go 10 by 10. Okay, so it's all zeros. So at some point, this is all just getting zeroed out. It might be here. So let's breakpoint in here. See if the normal vectors that we get are something that is in 0. Okay, so this is why they multiply this by 0.5 and then add 0.5. Is because the normal vector can be negative, but you don't want it to be negative. Alright, so now let's render this, see what happens. Rid of that. Control save. Render. It's still all zeros. Okay, so something's going on here. It's all rendering to zeros. So we are getting normal vectors. We are returning those. Maybe let's breakpoint after this operation here and see if this is what's messing it up here. You know, that seems fine. Okay. What happens if we hit continue here? Return normal vector, return normal vector. So there's a bunch of normal vectors here. Maybe our signed distance function isn't correctly returning, so image is a bunch of zeros. Color background, color object. Instead, we're returning the normal vector. Let's see if we accidentally messed up something else. Let's return color object here. See if we do end up getting Okay, it's just that it's very, very tiny. Okay. Let's make the image plane smaller. Let's go ahead and comment out this breakpoint. Okay, we have a slightly bigger sphere. Let's go ahead and put these things a little bit closer. Maybe make the sphere a little bigger. Let's make it 3 units big. That didn't really do anything. Let's make that bigger. Why is it a square? Alright. That seems like good values for that. Now let's go ahead and return our normal vector. Maybe there's some weird memory stuff going on here. Wow, I really wish I could solve this issue and then I could show you guys this pretty sphere. Empty image buffer. Let's do 128 by 128. Seems like a better compromise. That's good. Times equals 255, and then we have our breakpoint below that. Or let's just literally print image, and then we don't need to keep doing that. GitHub Copilot might be trying to save us here. It's saying, hey, you need to convert this to a uint 8. Okay. Now let's try. Let's make this 10 by 10. Okay. Let's go back to color object. We are getting the red there. Okay, so we're still running into this issue where normal vector dot copy doesn't numpy create copy of array. NP array a copy equals true. NP dot copy x. Okay, we're still getting these zeros. Where is that coming from here? Pixel color equals array march, and then we breakpoint here, and then let's look at what this pixel color is. So actually, let's just print the pixel color here. Okay, those are the correct colors. So now, when we're setting the image XY to that pixel color, we don't need this normal vector anymore. I'm pretty sure this was just a bunch of garbage. Bunch of misunderstood array stuff on my part. Yeah, okay, that still works fine. Print image XY. Ooh. We just killed everything. Okay. NumPy set pixel to color. Okay, so I think another way of writing this might be image x, y, all equals pixel color. I know what's going on. Oh, it's a uint 8. This first needs to be a float 32, right? Only then can it become intermediate colors, right? I think that might have been it. Yes, there we go. All right. Convert to uint 8-bit image 0 to 255. Get rid of that. And let's go ahead and make this big again. 256 by 256. Wow, that is a beautiful little square, little circle. All right, now let's go back to our ray marching. Okay. So now that we've merely made the color of the point on the sphere the normal, instead let's create some diffuse lighting, right? So we're going to create a light, and the light is going to shine on the object, right? And the angle of the light and the angle of the normal is going to determine how much light actually is visible on the sphere. So just return the color of the object. This is what we had before, where we just return color object. We're going to comment that out. This is what we had now, where we calculate the normal vector. Now let's make a third one here, which is calculate some diffuse lighting. So in this case, we're still going to get the normal position, but we're going to have a center of camera, center of image plane. We're going to have center of light. We're going to have a light that is at the same z position as the sphere, but maybe is a little bit higher. Let's say something like 4. So it's off to the top corner of the sphere. So the light vector, the vector from the light, is going to be the current position minus the light, current position minus the center of the light, and again, we're going to normalize this. Then we're going to take the dot product between the normal vector and the vector from the light to the object, and that'll give us the intensity, right? And then we are going to return the color of the object times the intensity of that diffusion. And let's see what that looks like. Quite crazy. So one thing to note here is that everything seems fine up until this middle point, right? And what's happening here? Well, what's happening here is that we don't have the notion of occlusion, and a dot product, right, isn't quite the right function here for taking the normal and the direction of the light, right? You see how actually the way that they do the intensity here, they take the max between the dot, between 0 and that. So they want sometimes the max 0.0 and then the dot product. So this means that whenever the normal is kind of in the same direction as the, or I guess the normal is in a different direction than the vector coming right on the ball. So there's a vector coming in, and then the normal is in that same direction. Then you basically just want it to zero out. You want that to be black. There you go. Perfect. That is very, very sexy looking. Distorting the distance function. Once we have the basic ray marching, we can nudge or perturb our distance function to create more interesting shapes. We can add a sinusoidal distortion to our sphere's FDF. Okay, so they say, hey, we have this SDS function. It's just returning to you the distance to the point. What if instead we have the sphere, and then we have a kind of displacement, and we'll just add some random signs here. np dot sign. Let's just do exactly here what GitHub Copilot is suggesting. That's a little bit different from the one that they have here in the examples, but I think it should be interesting. So then you just send the distance from sphere plus the displacement. Let's go ahead and do that. Let's see what we get. And it's a little weird looking oblong sphere. Ooh, this one actually looks a lot cooler. But the sphere is going to be different sizes. Let's also make it Z dependent. See what happens there. Ha! Doesn't that look really cool? It's trippy looking. Cool, so I'm going to go ahead and commit this ray marching in Python live stream. You can find this in the Betterer repo, of course. Helps you get started. Might have built a solid framework. Yeah, so maybe tying this back to kind of neural radiance fields. The same stuff is going on as we just did here, except we are not using this kind of hand-coded sign distance function. We are actually replacing this sign distance function with a neural net and then learning that to match specific 2D images from a variety of angles. So you do need a data set where you basically have an item and you can see it from a huge variety of different angles. Cool. That's all I got. Thank you for watching, and see you next week.